Hey, Matt Mathersum here with Math Madness. Thank you so much for joining us and being a part of the program today. Well, you know how we feel about it. We really do appreciate it. Well, for today's lesson, we're going to be combining exponential functions and word problems. And you thought you wouldn't have any fun today. Well, shame on you. So here we go. Let's just get right into it. We are faced with this intimidating word problem, and it says that if an insect population increases by a certain percent edge each month, show y is the number of insects represented by an exponential function. Well, what are we given? We're certainly given no numbers, no equation, nothing, right? We have to curate, cobble this, manufacture it all by our lonesome. How do we do that? Can we do that? Well, you already know the answer to that. We got a formula that's going to walk us right through this mess. So let's just get to this mess. I've underlined some of the highlights that I feel like will help us walk through this and create our own equation to solve for this. It says that a population increases by a certain percentage each month. Well, think about that real quick. What is that saying essentially? That we've got a population and it's going to be growing by a certain amount. So that's an indication of what? Time. So let's go ahead and set up a population function as a function of time. And how do we do that? Well, you know how to do that. That's just simply P of t. No big deal there, right? So we now know that our population is a function of time. That's a pretty common equation set up for when we're trying to find these types of word problems. You'll see this a lot. So don't panic yet. Here we go. Well, let's say, for example, that our initial population, they're saying our population increases. So our initial population, let's say that that's 1,000 insects for this example, okay? Well, we know it's got to be a rate of something, right? They're not giving us a rate. We have to show that rate because it says increases by a certain percentage. So what would that look like? Well, it would look like something along the lines of, let's just say that it's going to be 20% increase each month. So that would give us a 1.2 and raised to the t power. Well, how do I know that this is the correct function for this? Well, if I say t equals 0, and if I say t equals 1, and if I say t equals 2, and I plug these values into t, what's that going to get us? Well, let's do that real quick. Let me put in the 0 here into the t. Well, what's anything raised to the 0 power? That's 1. So that gives us 1,000 times 1. So we know that that gives us the initial condition of 1,000. Nothing has changed here. Well, what about a month out? Well, that's going to be our T1. So if we plug in 1 into the time here, what does that give us? Well, that gives us the 1,000 times the 1.2 increase, right? So how do we write that again? Well, that's just going to be 1,000 times 1.2. And in the future, it's just 1 month out. So that's just going to give us our 1. And last but not least, let's just go ahead and plug in our 2. And what does that give us? Well, that gives us this times itself, doesn't it? Right. So let's just say 1,000 times 1.2. And again, at time 2, because we're 2 months out into the future. Okay? Well, this, my friends, is a great example of an exponential function. It grows month over month over month. If I took this out to 3, 4, 5, 6, 10,000 months, we'd have the same formula, okay? That said, when we're dealing with calculus, and especially when we're looking at calculus textbooks, you might see something a little bit more formal. And let's just go ahead and make that a little bit more formal, if I can get this erased fast enough to make that happen. Sometimes the eraser wants to cooperate, sometimes it won't. Okay, here we go. I think I should have locked this down too. Anyway, all right, my wife is shooting this. So, honey, am I straight here? Is this okay? Am I still good to go? Okay, all right, she's giving me the go ahead. Here we go. All right, so something you might see more formal in a calculus textbook would be, let's say we want to do this a month out, okay? So let's take P of 1. And we want to know what this value is going to be a month out from now. How do we calculate that? Well, we have to know what our initial condition is, right? Remember in the previous example, I just gave us 1,000, well, we had over here 1,000 insects, right, is what we used. So we have P of 0, that's going to represent our initial condition, and that's going to be, right, it's going to have to be addressed with some sort of rate, isn't it? Well, what does that rate look like? Well, it might look something along the lines of this. You've got 1 plus k over 100 to the power of t. Well, you're probably thinking, Matt, that looks an awful lot like the compound interest formula. And you would be right for the most part. What this is, though, what we're going to be dealing here, what we'll be dealing with here in this particular instance is continuous growth, okay? That's why for the 100, we don't have the n. The n in the compound interest, as you probably know, is the times that it's compounded. Well, we're here with continuous growth per period, okay? That's what we're dealing with here. Okay, so let's go ahead and solve for month 2. Let's see what that would look like if we're trying to get month 2. And that would just be P naught. I'm substituting again for P of 0. You will see it written like this as well. P naught, or P sub 0. And how do we calculate 2 months out? Well, we take the first month and then we multiply it by the second month. So what does that look like? Well, that looks probably something along the lines of 1 plus k over 100 to the t times 1 plus k over 100. This is going to be a constant, right? Remember previously when I had us at 20%? Well, let's just say that we put the 20 here, we divide it by our 100. That's going to give us our decimal, and we take that decimal and add it to the 1, and we would get the 1.2. That's how we worked with the first set of problems that we had. All right, well, you can see that this times this is going to be squared. So let's go ahead and clean this up, and this will give you exactly what we're looking at for month 2. We have P naught times 1 plus k some rate over 100 times to the t power. All right, so we have solved for the exponential function, right? We can say at any time we want to calculate for t, we can just say it like this. We've got P naught times 1 plus k over 100. We all understand that, right? Our initial condition times this at t times, okay? But when we're talking about exponential functions, we like to see it raised to a base e. How can I raise this to a base e? Well, remember, any exponential function can just be raised to a base e. So how would I do that? Well, I would probably do something along the lines of, we'd have P naught e, right? Raised, here we go, raised to the natural log of 1 plus k over 100 to the t power, right? Right. Well, why can I do this? Well, because the e and the natural log, they obliterate each other, don't they? Yeah, they do. And you're probably thinking, well, hold on just a second. If these two obliterate each other, are you saying what we think you're saying? Yes, and let's just go ahead and address it right now. What I am saying is that this constant is equal to e raised to the natural log of 1 plus this constant. That's the 100. Apologize for my handwriting, but I just want to do this really quick. This is equal to this. Got it? That's it. Because these two obliterate each other. And now I'm left with this being equal to this constant, right? Okay. I'm going to erase a little bit of this because we've got a little bit more work to do here. And all right. And this will finish us up, though. Okay. Well, because of the log power, I can bring this t in front of the natural log here. And that's going to give us our function for time. Here goes. This is what it's going to look like when we're completed. It's just going to be P naught e raised to t times the natural log of 1 plus some rate over 100 at t time. I'm sorry, not at t time because I took the log power. It's e raised to the t times the natural log to this constant. Now, you may not like the way that it looks, and I agree with you. It is hideous. I would look away if I were you too. But this is the answer, and that's how these types of problems are solved. This one wasn't bad when you just take it step by step and you understand what they're asking, and that's all you can do is just a little bit at a time, highlight what you think is really important, and just work it out the best that you can. Well, that's all the time we have for here on Math Madness. Thank you so much for joining us. I am Matt Mathersum. I'll see you soon.